the attenuation coefficient. Yes, I think I've timed this all right. When the X-rays go through matter, their intensity decreases. So when they go in at an intensity of I naught, and the deeper the material, assuming it is uniform, that intensity decreases because of those attenuation mechanisms that we've just done. So the intensity drops down, and it drops like that. So this is a question, don't know which board it was, it doesn't really matter, they're all basically the same. So it goes in this case, at an intensity of 10 to the 3 watts per meter squared. And as the tissue, as you go deeper into the tissue, after 1 centimeter, it's down to 1 point wherever it is. Okay. Now, what we're going to have to do with that is we are going to have to work out this attenuation coefficient. And it's the same formulae as our radioactive decay, which was that. The number remaining is the initial number multiplied by this weirdo factor e to the minus lambda t. So lambda is the decay constant measured in per seconds if t is measured in seconds, which it is. Okay, and that equation mathematically explains the shape of that line. Okay, here's another one. Capacitor discharge. It's all the same thing. The voltage of a capacitor when it's discharging goes down like that, and the formula is that. There it is again. Q, the charge, equals Q naught, the original charge, times e to the minus t over RC, where RC is a time constant. But that's capacitance. We can look at water in a tube. The depth of water in a tube decreases like that exponentially, and you'll not be in the slightest bit surprised to learn that the equation for the depth is d naught times e to the minus rho t. The same sort of thing. And that e to the minus something is our exponential decay. The X-ray reducing its intensity due to those attenuation mechanisms. Now, if I show you that, there we have the formula I equals I naught e to the minus mu x. And the first question always says, what is the attenuation coefficient? So if you have a graph like that, what you do, I'm just going to look at the next slide. So I want a formula. Where's my formula? No. When you have a graph like that, if you think about your radioactive decay one, when you had a graph and you had to find out the radioactive decay constant, or a capacitor and you have to find the time constant, if you have got a graph like that, this is how you do it. So I'm just going to go through the maths. I'll do it up here. We've got I equals I naught e to the minus mu x. You could, if you wanted to, take some values from that and do something complicated. I can't be bothered. Watch this. I'm going to say that the half thickness at the half thickness, I over I naught equals a half at x a half, the half thickness. So let me shove that into my formula. So I have a half equals e to the minus mu x, a half like that. I'm going to take logs because I like that kind of thing. I'm going to take natural logs because it's e, logs to the base e. So I'm going to have the natural log of, I'm going to say 0.5 equals minus mu x half thickness like that. Easy peasy. I want mu though. Why did I do that? Let me just get rid of that. So I want mu, but little cheeky bit of maths. Natural log of half is minus natural log of 2. So I'm going to say natural log of 2 equals, get rid of the minus sign, mu x a half. So mu equals natural log of 2 divided by x a half. Well, that would be great if we could find out what the half thickness is. That's why they gave us this graph. It's obvious, isn't it? There is our incident 3. There is our half incidence. That is when the incidence has dropped to half. So I'm going to use my ruler here, and I'm going to go from there across to the graph to there, and then I'm going to go down from there to there. What's that? 0.82. 0.9, 0.82, 0.82 centimeters. So now what I can do is to put 0.82 into here. So that is natural log of 2 over 0.82, and we get our coefficient, whatever it is, like that. Okay, let's just have a think. There's our mad dog. Let's just have a think of what the units are going to be. I equals I naught e to the minus mu x. The units of the exponent there, there can't be any units of the exponent. It's just not mathematically possible to do e to the 4 kilograms, e to the 18 centimeters, e to the minus whatever. It can't have any unit, but always there are at least 2 things being multiplied together, which means that if we want the exponent not to have any units, then if x is in centimeters, then the units of mu must be in per centimeter, centimeters to the minus 1. So our centimeters to the minus 1 cancels out with our centimeters, and we have no units. It's simply a number, and you can do e to the number. That is legal. You can't do it any other way. Okay, so that's just an idea of what you get for your units. Now, the other thing that we've got is, so that's what you do. You always do that. You find mu from that graph using the half thickness. Then that's your attenuation coefficient. But it turns out that the attenuation coefficient, mu, is related, it's got something to do with the density of the material. Okay, proportional to the density of the material. So what is more important than the attenuation coefficient, which is called the linear, let me just get it, which is called the linear attenuation coefficient, units in this case per centimeter. You've got this thing, which is mu, oh, that should be subscript m, sorry, mu subscript m is called the mass attenuation coefficient. And to work out the units of that, if we have mu m equals mu over rho, and rho is the density of the material, let's work out what the units are going to be. Well, mu is going to be, I'm going to use SI units. Hope you don't mind. Doesn't really matter. I'm going to use mu is meters to the minus 1, and rho is in kilograms per cubic meter, but rho is on the bottom, so it becomes kilograms, it's on the bottom, per cubic meter, it's on the bottom, I lose my per, and I get that. So the units are, what happens is that cancels out with one of those, you get kilograms per kilogram meter squared, or meter squared per kilogram. Okay? You just have to calculate it. You don't have to do much with it. You just need to calculate it. So let's just have a look here at that. Okay, so all you have to do is do that. The linear attenuation coefficient divided by the density. Now I'm just going to share something with you. I don't like it when people put units in equations. It just makes me feel uneasy. I don't know why they did it here. It just looks horrible. I don't like it. You can do it if you like, don't get me wrong. That's not a personal attack on you if you do it. But why did they put 33 per meter over 2,700 kilograms per meter cubed? Anyway, you get that. And the units are, bump that, meter squared per kilogram. Right. Okay. Let's have a look at some questions. I'm not going to do the questions. I'm just going to show you how you can do them. Right. So, what's N? N is the intensity. So, we have the initial intensity is going to be I naught. So when it goes through material P, it has decreased a bit. And that is in effect the initial intensity as it goes into Q. So you use that equation there with, so I is going to be the intensity here. That is going to be given by I naught e to the minus P is that 0.6 times, what's the thickness of P? There it is, thank goodness I couldn't see it. 0.5, 0.5. And you do that on your calculators and you get a number. So it's something like, I'm going to make this up. I'm done it because I haven't got time. I'm going to make it up. I'm going to say 0.4 I naught. Make that up. Okay, now that is going to be the intensity as it goes into Q. So what happens is we get another loss. So we start with 0.4 I naught is our initial thing. So our next intensity when it comes out here is going to be 0.4 I naught times e to the minus 0.2 times another 0.5, 0.5 like that. And we get something else, another number, multiplied by 0.4, and that is going to give us n. Not got a clue what it is. Maybe I should have done it, but I'm just running out of time. I hope that's okay. If you're not happy with that, we can come back and do it later when nearly everybody's gone. Okay, next one. Much more complicated. Much more complicated. We've got that. Oh boy, there's a lot going on here. A lot going on. Right, we need to know how much X-ray energy is incident on the cyst in 30 seconds. So we've got to go through quite a lot of, I'm going to say quite basic physics. So first of all, when it goes in, it is that. So that's I naught. So I naught equals that. So what happens when it gets to the cyst is we've got that equals I naught e to the minus mu x. So it's gone 2.1 centimeters and the attenuation coefficient is that. So using that, those two numbers to put in there, we get some factor of I naught. I don't know what it is. We get some factor. Now, what happens is that is spread over this particular thing. Sorry, spread over the thing. And it has got an area there. It is, the cross-sectional area is that. So if you've got the intensity in whatever it is, watts per meter squared, because that's a unit of intensity, if you multiply by the area of this cyst, then you can find the power on that cyst. So you multiply that by the area of the cyst. Then to work out the energy, now that you've got the power, you multiply it by the time to get the energy. So it's quite a faff. It's quite a faffy question. And the answer is, there's the answer. Lots of different ways. What did it say? Okay, this is embarrassing. Many candidates even got the centimetre squared to metre squared wrong. That's embarrassing. Several candidates use the incorrect formula, energy equals power divided by time. What is going on? Which can be a common misconception. You did that in year 10. How can people be getting that wrong? I don't know. So when you're in there, just be cool. Be cool. Remember your formulae. They're on the formula sheet anyway. Don't panic. Maybe somebody panicked there. I don't know. Okay. And then the second part of this question is where I'm going to finish, which is name a different X-ray technique. Okay, so things weren't great. So there's a different X-ray technique to look at these things, which is computer axial tomography. Okay, so this is a CAT scanner. It is an X-ray. It's not positron emission tomography. It's not PET. It's a CAT. PET is different. We do that some other time. This is a computer axial tomography. So tomography is getting the picture. The computer works out what's going on, and the axial is the axis. You can see that the X-ray detector rotates about an axis with the patient in the middle. So there's your patient relaxing in the middle of this thing, which makes a phenomenal amount of noise. And that's an MRI scanner. Anyway, as it goes round, the X-rays form a sheet through the patient, and the detectors pick up the intensity at different points. The X-ray tube, the whole thing rotates. The X-ray tube shines up at different angles through the patient as it goes through, and all of these images from each of those positions is fed into a computer, and the computer works out what's going on. Okay, now it's quite straightforward. They're not going to ask you many things about it. So that is the mark scheme. What is a CAT scan? There you go. Well, that's it. Now, I would like to just, here we go. So where is it? It is in, I think, there we go. Advantages and disadvantages of. Okay, so AQA could ask you, give me the advantages and disadvantages of a CAT scanner, which does that, to a flat X-ray. There it is. Thing about X-rays is they are quite energetic, so they can ionize material, which isn't great. There we go. Right, I'll stop there. I'm pretty sure I've covered all of it. I'm quite pleased with that.
Now, the attenuation coefficient depends on the material. So it's a property of the material, just like the decay constant is a property of a particular sort of isotope of a radioactive material. So but the attenuation coefficient depends on the material. And you can see that if you've got different coefficients for the different materials inside a person, so the attenuation coefficient is much bigger or much smaller in flesh, watery substances in the body compared to bone, metallic based, inorganic. I mean, it's calcium, isn't it, in bones? But it's not just calcium, it's calcium compounds, but there's a lot of calcium there. That difference in the coefficient will make it so that X-rays are absorbed much more by bones and much less by soft tissues, and consequently you get contrast, and contrast is important. And when you're taking X-rays of things that are nothing but soft tissues, so for example somebody's guts, then you would get them for example, take a barium meal. So so a barium meal This is it's a contrast. Oh, can't spell. Medium. So you get the person to drink the barium meal, and the barium meal means that you've increased the contrast between the stuff that's in the gut compared to the stuff that's not in the gut, and it allows you to take pictures of what somebody's gut looks like with x-rays, because normally x-rays would just go through the squishy tissues and you'd just get a picture of somebody's spine if you tried to take a picture of their belly. So contrast medium is important from the point of view of attenuation of x-rays. It increases the contrast. It makes it more possible to diagnose things, and I'm no medic, so the sorts of things is beyond me. So that is how much a material absorbs x-rays compared to the material around it. So in general, the bigger your Z number, and Z in this instance is the atomic number of the material, the bigger your Z number, the more it will absorb the material, the x-rays rather. And the consequence is that most of the material in the body has a Z number. It works out to be an average of around about 7. Carbon, of course, is 6. Oxygen is 8. Hydrogen is 1. So it kind of works out to be about 7 for soft materials, tissues. If you've got hard tissues, so bone, that is calcium, which has a much higher absorption coefficient because it has a higher Z number. And you can improve contrast for the soft tissues by putting into those soft tissues something which has a higher Z number. And the two things that you need to know about are barium, which is introduced as a barium meal. So it allows you to swallow this, and then bits of your gut can be imaged very well. Barium's got a Z number, I think, of 56, I think, something like that. And the other one is iodine, which I think is 53. I wrote it down. Where did I write it down? Yes. Barium's 56, iodine's 53, and soft tissues are typically around about 7. Now, I don't know if you need to know this, but the mu, which is the absorption coefficient, is proportional to Z. This is the proton number, the atomic number, cubed. Okay, so typically soft tissues have got a Z of 7, whereas can you see barium and iodine, right? I mean, you know, it's massive difference. And the consequence of that is that the contrast is much improved. So these bigger Z numbers give you a much more absorption. And so it's like having the difference between a white bone and black soft tissues. So it gives you this ability to get a good contrast and consequently more detailed image of certain bits of you. The next thing to talk about then is the CAT scan. Now, on the OCR course, it's called a CAT scan. If you go and actually have one of these, sometimes it's just called a CT scan. Okay, the C and the T stand for computerized tomography. And if you use the A as well, it's axial tomography. Right, now, computerized just means you're using a computer to analyze the imaging. Tomography is looking at things in layers, slices. Okay, so And axial just means that it goes, it's perpendicular to the axis of person. So so you end up with it's like a big donut, and then your person, their head will be there, say, and their body will come out like this, and they're yeah, so you'll be able to see the rest of it, and they've got their arms usually down by their sides. Okay, so so this is so that and the person moves, you can move them in and in and in on an automatic table that will move you up and down. So this is a CAT scan or a CT scan.
A CT scan is an X-ray procedure that creates cross-sectional images with the help of computer processing. CT images are more detailed than conventional X-ray images and can reveal bones as well as soft tissue and organs. A conventional X-ray uses a fixed tube that sends X-rays in only one direction, while a CT scanner uses a motorized X-ray source that shoots narrow beams of X-rays as it rotates around the patient. There are special digital X-ray detectors located directly opposite the X-ray source. As the X-ray passes through the patient, they are picked up by the detectors and transmitted to a computer. Image slices can either be displayed individually in two-dimensional form or stacked together to generate a three-dimensional image that can reveal abnormal structures or help the physician plan and monitor treatments.
Each of the individual X-rays that you're exposed to is less intense than a regular X-ray. But because you get lots and lots of these, the overall effect is actually that CAT scan exposes you to more ionizing radiation. So they are not chosen for diagnostic purposes unless there isn't a better way of figuring out what's wrong. So so that is a CAT scan or a CT scan. I don't know, is there anything else I need to say about that? Not really, I don't think. Obviously, you can combine CAT scans with contrast media to help improve. And the great advantage of this is that you get sort of 3D imaging, which allows you to it allows you to see all sorts of stuff going on that otherwise you wouldn't necessarily. I mean, it's basically X-rays are shadow pictures. So unless you have some 3D imaging capability, you don't really get all that much detail from it. If you happen to have the angle right, you can detect a broken bone with regular X-rays, but you know, there's not a huge amount of diagnostic stuff you can do with that unless you also use the contrast medium, unless you also use the CAT scan. And of course, CAT scanners are incredibly expensive, so not every hospital will have one, but they are a very, very useful diagnostic imaging technique. I mean, graphy is a picture, it's an image, like photography and I can't think of another ography, but anyway, the calligraphy is an image, right? It's sort of writing on a page. But tomography is putting together slices to make an image. So you actually get a 3D image, and that's the point.
Me?
It's good.
Okay, so tomography means sort of slices. Okay, so you're putting together an image from slices, image from slices. Okay, so so what you do is you've got this spinning X-ray source and a spinning detector, and you've got it's like a kind of a white polo thing, and the person goes through it, and you can take pictures of any part of them, and if they have the correct contrast medium, you can get lovely contrasty pictures, and you can get great images, and you can do lots and lots of diagnostic things.
The correct name is actually iodinated contrast, and that is because it contains iodine in it, which is actually a heavy metal and shows up radiopaque or bright on CT imaging because it limits the amount of X-rays that are able to pass through. We can use this to evaluate blood vessels and to better evaluate organs. The other cool thing is this 3D reconstruction. So now you'll actually watch me set up the IV contrast and get it ready for a patient. We actually have these pre-made kits that we use to load the power injector, and this is the power injector. This allows us to inject the contrast without us actually being in the room exposing ourselves to the radiation. So since we use the console to set up exactly how much contrast and how much saline we want to administer, the power injector is really smart, and it'll actually draw up the contrast and saline to that exact volume. So now that it's all done, you'll notice I'm using a paper towel to take that IV contrast off, and that's because it's sticky, icky. Now this is the tubing that will connect from the contrast directly to the patient's IV. So you guys, this next step is so super important. Seriously, if you do not do this, you may end up killing your patient. I know you've seen it in movies. If you inject too much air, that is a dangerous thing. So you have to prime the tubing. Have to. Do not forget that. So the last step setting up the power injector is to pop on these warmers. And these warmers actually help with viscosity, which is the thickness of the contrast. The thinner it is, the easier it is to flow, and warming it thins it. So our power injector is prepped, and now we are pretty much ready for the patient.
Now, of course, X-ray won't go through bone, but it will go through soft tissue very much. And the consequence is that X-rays are good for diagnosing things to do with bones and good at diagnosing things where you can add in a contrast medium. They're not so good at diagnosing differences in soft tissues. And if you want to do that, then you're better off going for an MRI scanner. They have different issues, but they differentiate much more within the different soft tissues. MRI scanners give you images where there's water because it's the hydrogen atoms that are lining up. One of the things that you have to do is compare regular images, X-ray images, with a CAT scan. So they want advantages and disadvantages. Okay, so now, obviously, a CAT scan is great because you get lots of images and you can look at 3 dimensions and so on. And so that's really cool. It's a disadvantage of a CAT scan is that it exposes the patient to more X-rays. And of course, X-rays is an ionizing radiation. So the bigger the dose you get, the worse it is from the patient's point of view. And you don't want to be exposed to large amounts. Now, each individual image that a CAT scan makes is a low dose X-ray. They keep it as low as they possibly can, but you're getting hundreds of them all in one go because it's taking all these slices all in one go. So, so you get, in fact, the dose from a CAT scan is bigger than the dose from a single X-ray. And it does allow you to diagnose different things. So you need to, in terms of pros and cons, or advantages and disadvantages, the CT scan is a bigger dose. It's a bigger dose of X-rays, which of course ionizing. and but you do get 3D pictures, which is an advantage. So this is a disadvantage. And then this 3D pictures, which is an advantage. And you get lots of pictures, which might also be an advantage. It depends what it is you're trying to image. And then so you can diagnose. You can diagnose more stuff. Okay, whereas a regular X-ray, so if you break your arm, they're not going to give you a CT scan. But when my dad fell over and hit the back of his head, and they didn't know whether or not he damaged his neck because he knocked himself out, they did a CT scan of his the top part of his spine to check that there wasn't any damage there, that a regular X-ray couldn't see, because you can't see it from enough different angles because the bones in your neck are so complicated. So so you can see that they've got different uses, and there are advantages and disadvantages to both.